Welcome to qnawire.
Hello everyone, this is going to be the solution to problem 62, chapter 24 of Cottonell's physics. So let me just start off by saying that I think the solution that you're given to this problem is wrong, and hopefully I will be able to explain to you why. But the situation is the following. So you have a polarizer analyzer system like this, where you have polarizer, and there's a partially polarized light with some unpolarized intensity and some polarized intensity incident on the polarizer. And then some amount of light goes through, and then there's an analyzer, again, on which some amount of light goes through, and it's picked up, the light coming out on the far right is picked up by a photocell. And we're told that as you rotate the polarizer, you see a maximum and a minimum value of the intensity on the far right. So there's a caveat here. So obviously, if you have a polarizer analyzer system, then you can always rotate the two polarizers in such a way that their axes are perpendicular to each other, in which case there's going to be no intensity coming out on the far right. And so this is because, imagine that I had this incident light, which was partially polarized, then let's say, without loss of generality, that it is polarized, the polarization of the light is in the vertical direction. Then if I rotate my first polarizer such that its polarization axis, it makes 90-degree angle with the vertical, and so is a horizontal polarization axis, then I'm blocking out all the polarized part of this light. So I only have half of the intensity of the unpolarized part of the light coming through into the middle segment here. But now this light that goes in here is going to be polarized along the horizontal direction. And so if the second polarizer is a vertical axis, i.e. perpendicular to the polarization of the light that's in the middle, then there's no intensity coming out on the right. So this is not actually what the problem is asking you to find. What they want you to find is to say, what's the minimum amount of light that can come out of the first polarizer, and what's the maximum amount of light that can come out of the first polarizer, and associate the picked up intensity by the photocell to those intensities. So let's try and do that. So, okay, so for the minimum setup, as we've said, you're basically blocking out all of the polarization, all of the polarized intensity of the incident light, which means that you rotate your first polarizer until you reach a point that its axis, its polarization axis, is perpendicular to the polarization axis of the light itself. And so without loss of generality, again, assuming that the polarized part of the light is polarized in the vertical direction, if I rotate my first polarizer such that its polarization axis is horizontal, then I'm blocking out all of the polarized part of this light. And so in the middle here, I'm going to have that the intensity here is just half times the intensity of the unpolarized part of the light. Okay, so far so good. Again, unpolarized light, if it goes through a polarizer of any axis, half of its intensity is going to make it through, and it's going to be polarized along the polarization axis of the polarizer. So that's what's happening here. And so coming out, this light has an intensity of half S bar U and is polarized, and so it's oscillating in the horizontal direction. So I drew a little picture here just to make this more clear. So we have a vertical axis over here, and this is the direction of the polarization of the part in the middle over here. So now we want to project this intensity onto the polarization axis of the second polaroid, or the analyzer. But now notice that this is moving in this direction, right? It's horizontal. And so if the polarizer makes an angle of theta with the vertical, then I have to resolve my my horizontally polarized light onto this axis through 90 minus theta degrees. which is equivalent to saying that I'm going to be projecting away from the horizontal, away from the vertical. And so I can write this as the intensity incident on the second polarizer, which is a half S bar U, but now it's sine squared theta. So this is S min. And then let's look at the maximum case. So what's the maximum amount of light that can come out of the first polarizer? Well, this is going to happen in the case that the polarization axis is parallel to the polarization axis of the light. So in this case, the intensity in the middle is going to be half of S bar U, again, because it was an unpolarized component, but made it through. And then there's going to be all of the polarized intensity is going to come through. Okay, so now what's the situation this time? Well, here we have that this is the maximum amount of intensity that we can have in the middle. We have blocked out basically nothing except for half of the intensity of the unpolarized light. So now the wave in the middle is polarized, is an electromagnetic wave that's polarized along the initial polarization of the light. And let's say again that this is vertical, then if I don't rotate the second one, then I need to resolve this polarization that's pointing in the vertical direction onto the polarization axis of the Polaroid. So I need to project through the angle theta. And so projecting through the angle theta, that means that I have a half of S bar U plus S bar P. And this is all multiplied by cosine squared theta. So I'm resolving this vertical polarization onto the polarization axis, which is through a degree of theta. So now with these in hand, we see that S minimum is a half S bar U sine squared theta, which we can rearrange to find S bar U in terms of S bar min. And it gives us that S bar U is 2 times S bar min divided by sine squared of theta. And we can do the same for S max, because S max is a half S bar U plus S bar P, all multiplied by cosine squared theta. So plugging in the solution from here for S bar U in the second equation, we find that we end up with S bar max being equal to S bar min over sine squared theta plus S bar P, all multiplied by cosine squared theta. And now we divide by cosine squared theta to get S bar max over cosine squared theta. And so rearranging for S bar P, we just subtract from both sides S bar min over sine squared theta, and we end up with S bar P being equal to this value over here. So what we really have to do is we're asked to show that the percentage of the polarized light of the total, or the percentage of the polarized light's intensity of the total intensity is given by this formula, and it can be related to the S max and S min values through this. And so the question is this equal? So what we do now is we put in our solution for S bar P and S bar U in terms of S bar max and S bar min, which are all here. So putting that in, we have S bar P is equal to S bar P is equal to S bar max over cosine squared theta minus S bar min over sine squared theta here. And this is divided by S bar U plus S bar P, but S bar U was 2 times S bar min over sine squared theta, and plus this here. So we have S bar max over cosine squared theta minus S bar min over sine squared theta. Sine squared theta. And so we can see that this is 2 of this minus 1 of this, same thing. So this last one cancels the 2 from the first component in the denominator. So now we have 100 times S bar max over cosine squared theta minus S bar min over sine squared theta, all over S bar min over sine squared theta plus S bar max over cosine squared theta. So the next thing we do is we factorize 1 over sine squared from the numerator. So we have 1 over sine squared theta. And having factorized that, we end up with S bar max of sine squared theta divided by cosine squared theta minus S bar min divided by S bar min over sine squared theta plus S bar max over cosine squared theta. And so the next step would be to multiply this sine squared theta, or 1 over sine squared theta, into the denominator. And so with that, we're going to be left with 100 times S bar max of sine squared theta divided by cosine squared theta minus S bar min divided by S bar max sine squared theta divided by cosine squared theta plus S bar min. So in fact, I believe this is the right answer. And so this, again, I just got by multiplying the 1 over sine squared theta into the denominator. So the sine squared theta cancels the sine squared theta from the S bar min, and it combines with the 1 over cosine squared theta on the S bar max to give you S bar max sine squared theta over cos squared theta. And so I believe that this is the right answer. And so obviously, if you have theta being 45 degrees, such that sine theta is equal to cosine theta, then you recover the formula given in the book. But that's only a very special